share screen ili kasnije?
Možeš odmah, evo krećemo. Good evening and welcome to another episode of the Futures webinar series. Tonight we are learning about innovations in architecture, building technology research, and building science in contemporary practice. Our honorable guest is Ajla Aksamija, a renowned professor and researcher with an experience that spans across architecture, engineering, material science, and computer science. And I will let her introduce herself in more detail. Ajla, thank you so much for being here.
Thank you so much, Anna. It's my pleasure to be here tonight. Good evening, good afternoon, or good morning, wherever you are located. I'm so happy to be here today and to talk about innovations in architecture. So our agenda for today is, first I'm going to introduce myself. I will tell you a bit about my research and professional background. And then we are going to talk about innovations in architecture more in sort of general terms. And then I will show some case studies from practice, as well as research examples. And then at the end, we are going to have a questions and answer session. So as Anna mentioned, I'm an associate professor at University of Massachusetts in Amherst. I teach architecture. I'm an architect, but my research work spans between architecture, engineering, material science, and computer science. My research expertise focuses on high-performance buildings, computational design and digital technologies, building science, different types of advanced building technologies, new materials, and especially relating to facade systems. In terms of my professional background, so obviously over the last 10 years or so, I have been teaching and I have been involved in academic world, but I also have extensive professional experience. I'm currently working for a global architecture firm called Perkins & Will, and I was the founding director of one of the first research labs coming from architectural practice, Building Technology Lab or Tech Lab at Perkins & Will. That lab was founded in 2008. And at that time, it was the first research entity that was internal to any large-scale architectural practice. In terms of my professional experience, I had an opportunity to work on a variety of complex building types, including healthcare facilities, academic buildings, schools, commercial buildings, skyscrapers, different types of mixed-use buildings, everything but a single-family residential house. I would also like to introduce my research group. I'm currently advising 3 PhD students. 2 of them have background in architecture. One of them is a mechanical engineer. And I also had an opportunity to work with master students in the past and currently, and all of them are listed here. In terms of my published books, the latest one was published in 2016. On integrating innovations in architecture. That was the first book that looks into ways that we can integrate research and architectural profession, and also focuses on materials, new computational design approaches, high performance buildings. My second book was published in 2013, Sustainable Facades, and it focuses on facade systems and energy efficient design strategies. That book was also published in China and translated to Chinese language in 2018. And the third edited volume was on the future of architectural research, basically looking into ways that we can expand architectural research for the next 10 to 15 years. I'm also the founding editor of one of the first research journals coming from architectural practice, Perkins & Will Research Journal. I've also listed a link here. It's an open access journal that was initiated in 2009. It was one of the first peer-reviewed research publications coming from architectural practice. So I would highly suggest that you check it out and read articles, because it focuses not only on building technology and building science, but a wide variety of research topics relating to architecture, construction, design, interior design. So feel free to visit this website and read more about this publication. If you are interested to find out more about specific publications, research articles, I've also listed a website here where majority of the articles and published work can be downloaded. So feel free to visit this and learn more about my research. In terms of my professional experience, this slide shows some of the projects that I had an opportunity to work on. This building is a healthcare facility in Chicago, and I will actually be talking more about this particular project later in this webinar. These are examples of different building types, academic buildings, research laboratories that I have been working on. And the majority of my research work actually ties into architectural projects, and it's directly driven by architectural projects. So it is very applied in terms of research results and connection to architectural profession. And now let's talk about innovations in architecture and where we are currently and what is sort of the future of building technology in architecture and construction. So this presentation is not going to go deep into this book, but if you are interested to find out, you can certainly reach out to me. I would be happy to provide you with a copy of this book. But I will just talk about sort of the nature of innovative firms. What are the major drivers? What is the connection between research and development, design, technology? And something else that I would like to point out, when I was writing and researching this particular book, I had an opportunity to interview around 70 different firms located all over the world that focus on innovations in architecture. Some of these are well known, some of them are unknown, all different scales of firms as well, some of them very large scale, like Perkins and Will and similar, and all the way to two people firms, because I was trying to figure out what are the characteristics and properties of innovative firms in architectural profession. The results of that research basically showed me that the model for integrating innovation in architecture is basically presented here. Innovative firms really balance good design skills, excellent design skills, research and development, and then they also invest in terms of innovative project delivery, culture of the firm, and really try to integrate innovation as much as possible in their work. In terms of design, what I'm talking about here is particularly the role of computation and the new software programs and applications, as well as building information modeling as sort of a paradigm shift in architectural profession. In terms of the research and development, we have new materials, new construction techniques, construction processes, building technologies, and all of these influence innovation as well. And then innovative firms always invest in innovative practice, and that is achieved either through project delivery, meaning sort of collaboration with engineers, contractors, architects, other disciplines from very early stages of the design process. And also the culture of the firm is very important as well. Innovative firms try to build a culture where the innovation is welcome. Architectural practice and construction industry in general is a very risky business. It's very hard to innovate. So innovative firms always try to balance the risk and liability with the research and development and sort of application of new technologies in their projects. Something else that I realized during these interviews and kind of data collection for the book, what are the properties of the innovative firms? And again, regardless of the size or the market sector that they focus on, these are sort of the typical characteristics of innovative firms. Drive to basically inquire about new technologies, new construction processes, to analyze how these can be integrated into projects. very strong technical aptitude and connection to innovative building technologies and applications of those in practice, communication and dissemination of findings, research, innovative projects, and very strong connection to research-based design and integrated design, where basically the building technology, building science, and research-based design is implemented on a variety of projects from the earliest stages. Something else that is also extremely important in integrating innovations in architecture is essentially doing research and integrating research into design practice. And compared to some of the other fields like medical fields or computer science, I have to be quite honest and say that architecture is lagging behind, because there's typically sort of a gap between academic research and professional research, and we are not doing such a good job on integrating research into our everyday practice. So as I said, I was the founding director of one of the first research labs 12 years ago. At that time, there was not even a model of how to integrate research into design, into professional practice. And I had to try different things and figure out what basically works best for a large-scale architectural practice. So some of the findings of that work basically led me to develop a model that works well. So basically, there are three different models for integrating research into design practice: internal, external, and hybrid model. So the lab that I led was basically internal research entity with a design firm, and that also has benefits and drawbacks. The benefits are that the research tends to be very applied, driven by ongoing architectural projects, real projects from the practice, and there's a lot of connection between the design and research. The drawbacks are basically very short timelines and budgets and cost of research. The external model is basically when we have a design firm that collaborates with an external research and development entity, and that particular model also has benefits and drawbacks. And the hybrid model is where we have kind of a collaborative environment and collaborative practice between a design firm and research and development entity. So a good example of that would be a design firm opening up a nonprofit research entity to be able to collaborate with academic institutions, bring in external research funding, and fund the research and development work. Something else that I really need to talk about are the financial aspects and value of innovation. Many architectural firms globally right now are sort of struggling to figure out the best ways to innovate and to bring research and development closer to the practice. And I think a lot of architectural firms are realizing that it's necessary to actually invest in research. So obviously then in terms of the revenue and profits, we can kind of, the investments in research and development, we can visualize that almost as a negative revenue. But at the same time, there's an associated value for the firm. So no matter what the size of the firm is, what type of buildings they design, each firm that's interested in bringing in innovation and integrating research and development must sort of define why exactly are they doing that and what is the value for that particular firm. In some cases, the value might be monetary, new projects being brought on board, marketing efforts, and so on. And then some value might be sort of implicit, better designs, better relationships with the clients, and actually being leaders in architectural innovation. And in my personal opinion, that is a very valid sort of value point for any architectural firm. So obviously the impacts of the research and development are in terms of the revenues, architectural firms are integrating fully innovation and research and development tend to have certain returns on those projects, on those activities, while delayed adoption of innovation does not really benefit the architectural firms. So, a long story short, I think it's very important for any firm or anybody interested in bringing in innovation to really define what is the value of that work and what are the benefits for the firm or the broader society. So now, moving away from some theoretical discussions about innovations and sort of ways to bring in research into design, I would like to talk about a few case studies. First, from practice, to actually illustrate how research was driving either the design process, and then at the end, I'm going to show some true research examples on innovative technologies. So the first case study that I would like to talk about is Shanghai Natural History Museum, designed by Perkins and Will and located in Shanghai, China. This particular building is quite interesting. It was actually won as a design competition more than 15 years ago, and the design process lasted a few years, and then the construction process lasted quite a long time as well. But the project is actually very special. First of all, due to its site and location in the urban setting. So Shanghai is a mega city of several million people, high density, lots of skyscrapers. But this particular site for the building is located in the center of the city in the botanical garden, as you can see here in the image, as well as in the site plan here. So the location is actually quite special because the density of the city is so high that any landscape areas, any green areas in the cities are especially valued and cherished. So, and then the nature of this particular project, I mean, it's a museum dedicated to natural history. So the primary kind of driver for the design was to try to integrate the building into site as much as possible. So you can see here that most of the building facades, the roof, are basically vegetated roofs, and there is essentially a promenade, a slanting roof that connects the surrounding area here. So this particular building element was designed to bring in the roof down to the pedestrian level and to blend in into surrounding area. Another very important part of this project is essentially a courtyard, as you can see here, and a curved cell wall, basically, as you can see here in the plans and in the sections. This particular design element was integrated to bring in daylight to the building, because the building has 3 floors that are underground and 2 floors above ground. So this was basically, this acts as a large atrium, and then the cell wall was basically designed to mimic biological organisms and sort of natural history. You can see here the design of the courtyard. Traditional Chinese design techniques were used in the landscaping strategy for the courtyard, and basically it's supposed to blend in with the rest of the building site and the botanical garden. So this special curtain wall, the special cell wall, is a very large curvilinear structure that brings in daylight to majority of the building, but also provides shading. So this is a very complicated design element. You can see here in the section as well as the plan, it actually curves in 3 dimensions. And then the primary kind of design technique was to use sort of a cell structure and to repeat and create a pattern for the shading system, but also for the glass and the supporting system for this very large scale wall system. Another case study that I would like to talk about is Rush University Medical Center, located in Chicago. So it's located maybe 3 kilometers, 2 miles west from downtown Chicago, as you can see here. And it's actually part of a larger medical campus. So here's the building site. The butterfly-shaped building, what you see here, called the East Tower, basically houses emergency room, surgery, gynecology department, patient units, and so on. On the west side, there was an existing building built in 1950s. And then there was this special space in between the existing building and the East Tower that was actually designed after the East Tower was designed, the entry pavilion. The reason why the entry pavilion was designed later is because, as you can see here in this image, there's basically space between the existing building and the bed tower. And then after the design of this bed tower started, the clients realized that there was this empty space in between, and they wanted to create a very special place as kind of the main entry point into the medical campus and also within this building as well. And you can see here the scale. The East Tower is a very large scale building, close to 90,000 square meters in terms of area. And the entry pavilion is located here. So it's a relatively small part of the overall building, but it was designed in a very sort of special way. The primary goal was to try to bring in nature within the entry pavilion, and I'll talk about that a little bit later. But basically, this geometric shape, what we call a terrarium, was essentially an opening within the building to try to bring in nature inside. Green roof, a garden was also designed for patients, for staff, to again bring in nature to the building itself. Another really important kind of driving factor for the entry pavilion was to try to integrate as many sustainable and innovative high performance design strategies. And the reason for this was that one of the goals was to follow the Living Building Challenge standards. I'm not really sure how many people in Europe are familiar with the sustainability rating system, but it's similar to LEED, for example, or BREEAM in the UK. What's different about Living Building Challenge sustainability rating system is that it requires buildings to be net zero energy, net zero water, which is actually in complex building types very extremely hard to achieve. And it also has sort of a list of red materials or materials that shouldn't be used in construction due to their negative impact on occupants' health. So different strategies were used to try to achieve the Living Building Challenge for the entry pavilion, using renewable energy resources like photovoltaics. We also explored the possibility of using wind turbines to generate electricity. But the big driver was to try to bring in nature, as I said, through this terrarium. As you can see here, this is sort of a very special part of the building that it's landscaped, open to above. But the primary reason was to try to connect building occupants to nature, even within such a large scale hospital building. This is the green roof, several skylights that are providing daylight to interior space. We also looked into using a double skin wall on this. So this is a connecting bridge between the new building and the existing building, and I'll talk about that in a second. So in terms of integrating research and building technology and building science, for this particular project, there were a couple of sort of research objectives that were driving all of the research studies that were conducted. The first one was to try to determine how much shadow do we have, shadows on this green roof, because we are surrounded by a relatively tall building here and another building here. We also looked into daylight levels and conducted daylight analysis for the lobby and the terrarium. We also looked into solar exposure on different facade systems. We analyzed the double skin facade for the bridge connecting the two buildings. And then we also conducted a study to sort of investigate energy costs and system costs of a photovoltaic system that would be included on the project. So here are sort of slides that show the shadow analysis results. The primary driver was to figure out, will this garden be shaded most of the time? Chicago is actually quite cold in the wintertime, and then in the summertime it's not so cold, but then if we are shaded most of the time, it's going to be pretty uncomfortable in that outdoor space. So what we did is we used building information modeling and building performance analysis software programs to investigate position of the sun, and then how much shading we would have. So for example, these are the shadows on June 21st for different times of the day, from 7 a.m. to 6 p.m. So we found out that in the so like typical summer day, it would be shaded in the morning and late afternoon, but most of the day we would be fine. And this is the same study, but essentially for typical winter day, December 21st. I also mentioned that the daylight analysis study was performed for the lobby space and the terrarium. And the reason why is because the research question was, are we going to have enough sunlight, basically striking the ground floor here for any types of plants to survive? So the lobby space of the entry pavilion is quite high. It's essentially equivalent to a 3-story building, but it's completely open. So if you can imagine, okay, it's open to above, we have some landscaping, we have trees growing within the terrarium. Are we going to have enough sunlight to penetrate here for any plants to grow? So here are the results of the daylight analysis. Here on the left side, you see simulation results basically on a ground level in a floor plan view. And here's basically vertical sort of section view and distribution of daylight levels. So the interesting finding was that we would have too much daylight and it would not be a problem. So the results of this study were also used to actually optimize the choice of glass and the design of the skylights. One of the skylights was also eliminated because the simulation results show that it would be too bright inside the space. And these are the final sort of after construction photos. You can see that it's pretty day lit. You can see sort of the landscaped area here and the nature. And this is not supposed to be kind of occupied by people, patients, or visitors, but it's really meant to be observed, bringing in nature within the lobby space. And here are the final photos of the roof garden, the entry pavilion, and the bell tower itself. As you can see here, this is basically the top of the terrarium. It's pretty high. People can still actually look down and see what is going on in the terrarium. And these in the back are essentially skylights that are bringing in daylight to inside the space. Something that's quite interesting about this particular building, when it was designed, basically the ground level and the emergency room, the spatial organization was designed to function well, even in case of bioterrorism or in a case of a pandemic. And over the course of the last 2 to 3 months, this particular hospital turned out to be basically state-of-the-art facility in the US for treating coronavirus patients. CNN made a documentary about this building, and then a lot of hospitals right now are looking into this particular hospital and how it was designed and the spatial organization to try to replicate that in future healthcare facilities. So now I would like to move on to some of the research examples. So basically research studies that are more, that are not particularly driven by a specific architectural project, but addressing new trends, new technologies, new materials. So the first project that I would like to talk about is it's an adaptive reuse and net zero energy design building. So the building location is actually very close to university where I teach. So Amherst is here, and Holyoke is maybe a 20-minute drive on the south from Amherst. This particular climate is actually very similar to Bosnian climate. So heating dominated, uh, long winters, lots of snow. Something really interesting about the city of Holyoke is that it's a city that over the last 50 or 60 years has seen a drastic decline in terms of the economy and industry, and it's very representative of many cities across the US that were in 1800s, 1900s, primarily industrial cities, but since the early 20th century, and especially after the Second World War, have seen a decline in the economy. So, for example, Holyoke right now has about 80, 90,000 people living there, and then in late 1800s, early 1900s, it had basically twice the population, like 160,000, 170,000. So the building site, and the reason why we chose this is because this particular building is a good representation of what's happening to a lot of buildings that were built in 1800s and 1900s that were used mostly for production, factories, paper mills, and so on, but have been abandoned. And so we use this as a case study, how we can basically retrofit an old building like that, bring it back to life, change the purpose and function of the building, and also the focus was to try to achieve the net zero energy design. So net zero energy design is basically, it means that the building has renewable energy resources that are integrated onto the building site, such as photovoltaics, wind turbines, fuel cells, geo-exchange systems, and so on. So net zero energy buildings basically produce as much energy on an annual basis as they use. So we use this building as a case study just to explore how regenerative design approaches can be used on a variety of industrial building types to try to change the function, but also to improve the performance. So here's the building in red. It's actually one of the tallest buildings here. Connecticut River is right next to the site of the building. This side of the site is very industrial, a lot of warehouses, industrial buildings, while this particular side is basically mostly residential. And here's a close-up site plan of the building itself. There's a bridge near the site. There's also an existing railroad, as you can see here in blue, that's not operational anymore. And these are the different views of the building. The building right now looks like this. Very bad, boarded up. Right now, only 20% of the building is used, as you can see here, for some commercial purposes, but the majority of the building itself is boarded up, unused, in very bad condition. So we wanted to take this as a case study and see what we can do to change the function and redesign and change the purpose of this, bring back life to the building, but also the area around it, and also to meet net zero energy goals. So this was our proposal. This was the redesigned building. We analyzed the structural system of the building first. It was interesting that the building was actually retrofitted several times over the last 100 years, in 1920s, in 1940s, in 1960s, and the structural system was inadequate. There were some parts that could remain, some parts that would have to be torn down because they couldn't withstand any changes to the structural system. So then what we did is we basically proposed to keep what we could, eliminate structural systems that were not adequate, and then we added essentially a commercial floor, as you can see here, of new program to be integrated with the existing building. And here's another view from the river. So basically, this diagram shows different strategies. This is the existing building, and then it shows what was changed. So we removed some of the vertical circulation cores, changed the major entrances into the building. We added this major element, which would be sort of an office floor to the building. We added some courtyards, green roofs, and we try to preserve as much as possible of the existing building, as I said, but also we changed the function and added new functions to the building, such as a retail store, some residential units as well. So here, this diagram shows basically vertical transportation, shading system that would be used, location of different green roofs and courtyards on the ground level and upper levels as well. And because we changed the function of the building, initially it was only a commercial building, but we brought in residential apartments as well. So this would be reconstructed into a mixed-use building. We also had to determine how the circulation would work for the commercial side, for the residential parts, but also for the office tower on top. And here are the elevations showing the materials, the existing building here, and then the new component added on top. This also allowed us to bring in green roofs and these landscaped areas at different heights of the building. And then this diagram shows the passive and active design strategies in terms of sustainability measures, because for net zero energy design, we have to, first of all, reduce the energy consumption of the building as much as possible using first passive design strategies, looking to orientation of the building, solar position, shading, and then advanced building systems like energy efficient HVAC systems, renewable energy systems, and so on. Since we started with the original building, we couldn't really change the orientation. That's a lot easier to do with new construction and new buildings. But at least we looked into each building orientation and added shading devices where they would need it. We proposed to do green roofs, as I said, first of all, to improve the thermal performance of the building, to make the building more beautiful, but also to improve the stormwater management system. And then we proposed to use the rain garden to irrigate the rest of the site. And we would be collecting the rainwater within the building and also using that to irrigate the site as well. And then we proposed to use renewable energy systems, several of them, wind turbines, photovoltaic panels, biomass, and also hydro energy to meet the net zero energy goals for the building. So here are results of the energy modeling. So high performance buildings and sustainable design is different than traditional design. When we're trying to improve the energy consumption of any building, and especially trying to meet the net zero energy goals, energy modeling and building simulations, building performance analysis, these procedures need to be included from the early stages of the design process, from conceptual design to schematic design and design development. So during the design process of this particular project, we did essentially two different models. When we redesigned the building, we did the initial model. As you can see here, all of the inputs and assumptions for the energy model to establish the baseline energy usage. And then we looked into maximizing energy efficiency measures and improving facade systems, insulation of exterior walls and roofs, occupancy schedules, using advanced energy efficient HVAC systems to quantify what is the lowest energy consumption that we can achieve. And basically, these are all the inputs for the second alternative model. And these are the results for the initial design and the alternative design, basically quantifying the electricity and gas consumption. So these were basically our final numbers. So I'm sorry I didn't convert this into metric system, but the initial result was the energy usage intensity would be around 120 kBTUs per square foot. When we applied all of the high performance and sustainable design strategies, we would cut the energy usage more than half. So achieving net zero for a building that has this energy consumption is actually a lot more cost effective than higher energy consumption. So in terms of the renewable energy resources, we integrated 4 different types of renewable energy resources. Photovoltaics on the roof of the building, as you have seen in some of the renderings and diagrams. Also, vertical axis wind turbines on the roof of the building, but also within the landscaping. We also considered using biomass as a source for heating the building, because Holyoke is actually surrounded by a lot of agricultural land, so biomass as a heating source is readily available in this area. And then the third renewable energy resource was hydro energy. It's interesting that city of Holyoke 150 years ago actually had a lot of hydro turbines installed in the water systems of the city, and those turbines are not working anymore. But we were considering of essentially bringing one of those back to life and providing renewable energy for this particular building. So these are the final calculations in terms of the output for photovoltaic panels, and then basically breakdown of all of the renewable energy systems and how we would meet net zero energy goals. So roughly 45% of the energy needs would be met by photovoltaic panels, 20% by wind turbines, 12% by biomass, and 23% by hydro energy system. Another case study that I would like to show you today is investigation of the parametric building skin design and digital fabrication. This particular research was done almost 9 years ago, but I think it's kind of interesting because it shows you what happens to these kind of long-term studies and research. So our objective here was to investigate parametric design methods and integration with building performance analysis procedures, but also we wanted to investigate digital fabrication techniques like laser cutting, CNC milling, and so on. And we chose an actual project, a real project located in Chicago. And we focused on the building skin design, basically coupling different advanced software programs and digital fabrication techniques to design sort of a high performance facade system for this building. So the original building is 8 stories high, as you can see here. It was built in 1920s and it functioned as a cold storage facility. So imagine almost like an 8-story, very large fridge for storing food. So the client for the actual building bought this building and wanted to convert it into an office building. They wanted to. Here's another view from the other side. They wanted to essentially keep the building structure as it is, but change the building facade and repurpose the entire building from a cold storage facility into an office building. So this case study was a perfect project to investigate innovative techniques, new computational tools, and parametric design. So this was our process. So typically simulations and building performance analysis in design process, even today, are not highly integrated with the design. So what typically happens in design practice is that architects come up with a plan, initial documentation for the project, they finish conceptual and schematic design, and then they give off documentation to engineers who then calculate and do energy models. But the problem is at that time, it's actually too late. So even when we get back results from the engineering side that quantify energy performance or performance of the facade system, it's actually too late to make any meaningful changes to the design process. So the earlier the building performance is integrated with any project, the results are better. So what we did here is basically we wanted to kind of explore this digital integration and digital process where we would come up with a design concept for the facade. Then we would perform simulations and modeling, for example, to understand solar radiation on different orientations of the facade system. And then we would use that data to drive the geometry of the facade system, and we would use parametric tools. So rather than manually changing 3D model, redesigning, different design options, we would basically use the data from simulations to drive the design decisions, but also so this would happen in kind of a semi-automated way. So then this was basically the process. We started with kind of pre-design, gathering information, because it's an existing building, looking into current conditions, what can be done, context, and so on. And then we use different tools to explore the designs and initial geometries, Rhino, Revit, 3D Max, Maya. And then we perform simulations, such as looking into solar radiation data for different building facades, as you can see here, or modeling wind around the site. And then we would use that data through essentially parametric tools like Grasshopper, Maya scripts for Maya software, some custom tools for BIM software programs to design the facade systems. And then the last step was to essentially fabricate components and mock-ups of the facade system. So here's one example. This particular design solution basically responds to solar radiation. So these are readings from solar radiation building performance analysis tool called Ecotect. So this is basically for the north side. This is for the west side. This is for south side and east. So we use these tools and the data coming from the software to actually design a system. So this facade system would consist of a glass fiber reinforced concrete, or GFRC. That's also kind of an emerging material that's a lot stronger, structurally speaking, than conventional concrete. So you can basically obtain thinner profiles and more kind of complicated shapes than with a traditional concrete. So the building facade would have GFRC panels. As you can see here, the GFRC panels would also provide shading, but then the sizes of windows would be varied depending on each orientation and how much solar radiation we would have. So for example, this would be installed on the west facade, as you can see here, kind of deeper design elements, facade elements, more shading, less windows. And this would basically be installed on the east and north facade, where we don't need as much shading. And these are some of the digital fabrication techniques. So essentially we built forms and then use plaster to build kind of real scale mock-ups, prototypes of the GFRC panel. The last case study from research that I would like to show you is on new intelligent facade systems called thermoelectric facades. So this is an ongoing research project that started roughly 5 years ago. We are still working on it, but I wanted to show you as a good case study that kind of illustrates first of all, collaborative research between architecture and engineering, but also how we can integrate some of the emerging materials and technologies in architecture, and how do we conduct research for those. So thermoelectric materials are smart materials. They have been around for almost 100 years. Like, this particular phenomena has been known in scientific fields for a very long time, but commercially available materials have been around for the last 20, 25 years or so. So these materials basically produce temperature gradient when you apply electricity to them, which is called the Peltier effect, or they can also generate voltage or generate electricity when exposed to a temperature gradient, which is called the Seebeck effect. So this particular phenomena has been known for a very long time. But basically, the commercial thermoelectric modules have been around, as I said, for roughly the last 20 years or so. So this is how they look. They are typically 4 by 4 centimeters big. They are robust. They are relatively cheap as well. So although they have been around for a relatively long time, there are only a few applications. So, for example, these materials have been used in space applications, in automotive industry, but not so much in architecture. And this was our idea. So since these materials basically function when you have a temperature gradient, buildings are a perfect application for this, because when we think of any building, we always have certain temperature inside that building, and then certain exterior environment. No matter if you're located in a heating dominated or cooling dominated climate, there's always a temperature difference and gradient between the inside and outside. So our idea was to try to integrate this into exterior wall systems or facades, and just based on the temperature gradient between the inside and outside, use this system to generate electricity or provide heating or provide cooling. So a beautiful thing about thermoelectric modules is basically based on a control system that you can integrate with these thermoelectric modules. You can provide heating or cooling or simply generate electricity. But it was interesting that nobody before thought about including these materials in facade systems or in buildings. So what we did is we initially developed some ideas how exactly this could work. How can we couple this with facade systems? Even from the beginning, we knew that there must be some sort of a conducting mechanisms between the inside and outside, because for majority of facade systems, you always want to block heat transfer. We typically use layers of insulation to try to improve actually reduce the heat transfer and improve thermal performance of all systems. But in this kind of active part of the facade system, we really want to conduct heat as much as possible from the inside to the outside. So we knew that there must be some sort of a conducting mechanism that couples the inside temperature and the outside temperature. We also knew that there must be some sort of a heat sink included, because thermoelectric modules, they do provide very high temperature or low temperature, but without dissipating that heat deeper into the space, they would not be really applicable to building scale. So what we did is we then actually designed and developed prototypes and tested prototypes. So these were kind of a couple of different ideas how this system could work, but we ended up designing and building these two, the direct contact and sort of a steam transfer mechanism. And here are the initial prototypes. So this was the first one with a thermoelectric module that would be installed kind of inside the wall system, and small heat sinks on the inside and outside. And this was the second prototype, basically with much larger, so thermoelectric module would still be here in the middle of the wall, but we would have larger heat sinks on the inside and outside to try to basically improve the heat transfer through the thermoelectric modules. And the reason why we decided to actually design and build prototypes is because this system does not exist. Building simulation tools and building performance analysis software programs that we currently have available are not built basically to analyze this. So that's why we had to start with an experimental study, which typically is usually the last step of any research process. In this research study, that was the first step that we started. So here are basically just initial measurements for the thermoelectric module alone with a small heat sink, for the first prototype and the second prototype. So what we did is we used a thermal chamber basically to control the temperature. Then we applied the thermoelectric facade, as you can see here. So the thermal chamber was used to essentially control the temperature, to kind of represent the typical exterior, varying exterior temperatures. Again, I'm sorry I didn't convert this to metric system, but 0, 30, and 60 Fahrenheit, for example, for heating, and then 60 and 90 degrees for cooling. And then the inside was basically kept at the room temperature. And then we use the thermal camera to actually measure the outputs, the heating and cooling. And it was interesting that our results were actually a lot better than we thought they would be. So our hypothesis was that they would probably perform well in the heating and cooling modes, depending on the temperature gradient that we have. But the results, the initial results, were really surprising and gave us great initial results to basically extend the study and try to develop real facade systems. So what you see here are kind of, this is the extension of the study to try to integrate this system into existing various facade systems for buildings. So for example, here, the thermoelectric component would basically be this. So for example, this can be any sort of solid wall facade system, but then the thermoelectric or the active system would basically be this. And then if we can use a metal shading device, vertical shading device like this, that could also act as a heat sink. And then by transferring the heat to the thermoelectrics, they would provide heating or cooling. And then on the interior side here would be a radiant panel that would provide heating or cooling to the interior space. In this example, this is basically for a rain screen facade application where we would have metal cladding. So for example, the rest of the facade system is typical rain screen facade system with metal cladding, but this would be the active part of the wall system, and the metal panels here would actually act as a heat sink. The temperature would be basically transferred to the thermoelectric modules, and then the radiant panel here on the inside would be providing heating or cooling. And then in this case, this is a typical curtain wall application. And then these parts of curtain walls are called spandrels, and they're typically used to provide sort of solid parts of a curtain wall system, either to hide the floor, slab, the mechanical systems kind of underneath, or to improve the thermal performance of the glazed facade system. So here in the spandrel application, we could still have a metal panel that's nicely integrated with the rest of the facade system, but then this would be the active part of the curtain wall, providing heating and cooling. And we also built real scale prototypes basically of this system, and our future work is basically to test the performance of those systems. And here I will show you a video, but I need to stop sharing for a second and switch to so this video basically shows a bit of the research and lab and our process.
Thermoelectric materials are a special type of semiconductor material. To my knowledge, thermoelectrics have never been used in building facades.
That's 8-inch thickness. The system that we're developing and researching can certainly provide heating or cooling, plus energy generation.
The thermoelectric module inside the facade is thermally coupled directly to two heat sinks, one on either side of the facade. So that allows the thermoelectric module to, in a sense, talk to the environments on both sides of the wall and mediate between them. We conducted experiments in our lab primarily aimed at determining the optimal operational conditions and efficiency of the thermoelectric module. So I was very surprised by the overall efficiency. It was pretty efficient across the board.
The benefit of this particular system is that it can be included in any building type. Reducing energy consumption by, let's say, 50% is doable with the current technologies that we have. Smart technologies, smart materials, and smart systems can even push that boundary even more. Okay, so I'm going to go back now to the presentation. So the last few slides that I wanted to show you are just some examples of the teaching and sort of my attempts to bring Bosnia and Herzegovina to UMass students. So this particular class, I was teaching this class 4 years ago in 2016, and it was my first attempt ever to bring a bit of Bosnia into my classes and what I'm teaching. And at the beginning, I was actually quite afraid, how is that going to turn out? Because first of all, you know, architecture is all about sort of sense of place and being connected to the site and history and culture and tradition. And it was interesting to me, how would I try to teach students who are based here, who might be, you know, from anywhere in the world, but how could I do something from Bosnia and particularly Sarajevo? So what we did is there were a couple of exercises basically conducted that semester. We had about 30 students, and these were third year undergraduate architecture students. The major project that the students were designing was essentially a new design project for the Ars Avi Museum of Contemporary Art. And we were actually working with the Ars Avi leadership, with the director, artistic director on this project. So they were involved with the students as well. And then the first kind of beginning of the semester was all about trying to convey the culture, the history, the tradition of Bosnia to students. And it was really interesting to kind of explore with the students. Many of them have never heard or were vaguely familiar, you know, where exactly Bosnia is located in the world, but they didn't know more than that. So the initial project was to try to create sort of a memorial. And then the last project was to design the sort of a building for the Ars Avi Museum of Contemporary Art. The project site was located right along Miljacka River in Sarajevo. This is Vrbanja Bridge, the Parliament building. At that time, this was just a parking lot that we selected for the site. Maybe there's something built right now on this site. I don't know, it's been a while since I've been to Sarajevo, but this was basically our site. So students explored the tradition, culture, history, architecture, and I just wanted to show some final examples and what they came up with at at the end of the semester. So this particular student chose to basically sort of look at the Sarajevo roses and look at how, you know, what types of shapes and geometries and the impacts on the built environment this very powerful memorial had, and then translated that into the built form. And his idea for the museum was to try to use the Sarajevo roses as a concept to basically translate that into museum. And here's the site and kind of his design. This was the memorial that he designed, and then sort of the spatial organization of different galleries, circulation space through the building, and just a rendering showing kind of the night view of the museum and the Sarajevo city center in the background. And I love the figure here. This could really be my grandfather standing and watching over the museum. These are some of the elevations. What you see here was basically a memorial that he designed that pedestrians could walk through and then access the museum. This was another student, and her design concept was basically to design a building that sort of reflects the place where the East meets West. And I'm originally from Bosnia, but I've lived a very long time in the US. And then through the eyes of my students, I kind of rediscovered the history and culture and tradition and architecture. And I think majority of the students were really fascinated by Sarajevo and Bosnia in general as being this unique place in Europe where the East really truly meets the West. And this particular student chose basically that as a primary concept and designed the building form to kind of capture that concept. And here's just some renderings that show the interior space. And then the last student that I chose to show you basically used the mountains as kind of a landscaping and primary kind of elements of Sarajevo to translate that into the design of the museum. So this is the rendering of her proposed design and the floor plan, and then the interior rendering kind of overlooking the Parliament building. So I just wanted to show you as an example that not only is it important to sort of bridge the gap between kind of the outside world and Bosnia and Herzegovina, particularly through these webinars and through this foundation, but we also have a lot to offer to the outside world. And I hope that in the future, I might do more projects like this. And then the last thing that I wanted to mention, I will actually be teaching a summer course that starts on Monday. For those of you that might be interested in the design of sustainable high-performance facade systems, this is the first time that I'm offering the course. It will be completely online for 6 weeks, starts next Monday and goes until June 26th. And there are 2 sections, one for graduate students and one for professionals as a continuing education course. So this is where you can find more information about it. So at the end, I would just like to offer some concluding remarks. When it comes to the innovations in architecture, we are currently kind of entering the era of unprecedented changes. And this is driven by several different really important factors. Environmental challenges, sustainability challenges, economy. Over the last few months, pandemic as well has influenced the way that we work, the way that we sort of inhabit our built environment. At the same time, we have all of these technological advancements, such as new materials, building technologies, computational design methods, building information modeling, digital fabrication. These were not around 20, 30, 50 years ago. And they're changing so much, and they are really truly impacting architectural engineering and construction industry at sort of a great scale. So integration of research and development, building technologies and building science is really essential for innovative practices and any architectural practices at all. So, and the last thing that I would like to point out is kind of this notion of interdisciplinary research, interdisciplinary work. I think one of the primary drivers in my career has been kind of this quest to try to answer questions, to try to really address complex issues. The reason why I even chose to go into research and why I chose to focus on interdisciplinary work is because I realized that the only way to answer some of these really tough questions was if I go outside of architecture, if I go into other disciplines that are related but different, to try to find answers to the questions that I had. And I would like to offer, especially for students who are listening, I would like to offer a piece of advice to always try to go outside of your comfort zone, learn from other disciplines, try to bring back to your own discipline whatever you learn from other fields. I think that can only benefit your academic work as well as future career. So with that, I would like to thank you and open up for questions and discussions.
Hi, thank you, Ayla. So far we had two questions and they were really great ones. We have four now. The first one is, are relatively old buildings a potential hazard in case of earthquakes? Old buildings in the Zagreb city center were quite damaged recently in an earthquake.
Yes, I think that's an excellent question. And yes, they are. It depends on when exactly they were built. So I think buildings that were built, let's say, 50 years ago or more are definitely a hazard, because at that time we didn't have codes and standards for seismic zones. So we have areas of seismic activity in Bosnia, in Croatia, here in the US, mostly on the West Coast, California, and so on. There are certain codes and requirements that we have to follow when designing buildings in those areas. So buildings that are more than 50 years old typically did not follow those rules because they're relatively recent. So when we are trying to retrofit buildings like that in seismic areas, we really have to pay close attention. We have to analyze the existing structural system, capacity. What are we trying to do? What are we trying to retrofit? Are we adding, new structural loads, weight to the building, or is it mostly cosmetic changes and retrofits? So it's a very kind of complicated activity, but necessary. And then, especially if we are trying to add to an existing building. So, for example, the case study in Holyoke that I showed, we performed structural analysis of the existing building. The reason why we chose to essentially tear down vast majority of the building was the structural system was not adequate at all, and we're not even located in a seismically active zone. So we always have to pay attention to that and do an analysis, figure out what is going on with the existing building, and then see what can be saved and then what else we can improve.
The next one is, do you have some kind of electrical energy storage like batteries in these buildings because renewable energy sources are not reliable, or are they connected to the grid?
Yes, that's also a very good question. And there are basically two different ways when we're integrating renewable energy systems into buildings. We can have off-grid buildings, or we can have buildings that are actually connected to the electrical grid. And the decision is typically driven by where exactly you are located, the stability of the grid, who is the energy provider, do they have programs like that? So, for example, here in Massachusetts, vast majority even of the supplied energy to our buildings is renewable, because the state of Massachusetts is investing a lot of money and resources into renewable energy resources. So even the energy that's delivered is, I don't know the exact percentage, but certain percentage is renewable. But for example, if you have photovoltaics, and by the way, another thing is that a lot of residential buildings in Massachusetts are currently integrating photovoltaic panels and selling back the energy to the grid. So for example, let's say a building can integrate photovoltaic panels, energy can be produced, it can be used by the building, or if there's excess energy that's not needed at that moment by the building itself, it can be sent back to the grid and then sold to the energy provider. So these are kind of buildings that integrate renewable energy resources but are connected to the grid. There are also examples of buildings that are completely off-grid, that have renewable energy systems integrated, wind turbines, photovoltaics, and then a storage system that is basically just for that building itself, and it's not kind of integrated with the grid. And then, for example, here in the US, it's basically for buildings that might be located in rural areas or for basically areas where the energy providers um, um, do not have agreements with kind of residential sector for creation of renewable energy system. So another kind of interesting thing is in Bosnia, the energy provider is a state-owned agency, as far as I know. Here in the US, it's not, it's a private company. So that also has a lot to do with kind of the supply and demand, production, and so on.
Okay, next one is a really short question. Is the course you mentioned gonna be free?
Unfortunately not. So for students, I think it's a little bit more expensive, but for as a continuing education course, I think it's actually a lot cheaper. And the reason why I decided to teach this course is we recently moved to online education in the last 2 months because of the pandemic. And I have been thinking about offering that course because I have been teaching that course for the last 7 years to graduate students, but not for professionals. And I have been, over the last, 5 years or so, I have been getting so many questions from professionals. Would you be interested in offering something like that? So that's the reason why I decided right now it's something that I can do in the case of this pandemic. So for professionals out there, it's a little bit cheaper to, and again, I have nothing to do with that. My university sort of says that.
That's definitely going to be useful to many, I believe. We have 3 more questions. The first one is, as a civil engineering student, I didn't get the impression that engineers in Bosnia and Herzegovina pay much attention to interdisciplinary research as a way of improvement. What is your take on that?
Can you repeat the question? You were kind of breaking up a little bit, please.
As a civil engineering student, I didn't get the impression that engineers in Bosnia pay much attention to interdisciplinary research as a way of improvement. What is your take on that?
Excellent question. And I think it's not only in Bosnia and Herzegovina, I think it's present in other countries as well. And I think it has to do maybe a bit with the fear of unknown and going outside of your comfort zone. So during education, during our academic career, when we're studying, we're typically taught to think one way. You're taught to, you learn vocabulary that is associated with one discipline. You learn kind of the ins and outs of that discipline. And I think by default, people are generally not comfortable going outside of their own disciplines because it's complex, it's different. But at the same time, I think for innovation and for sort of improvement, for new technologies, for even if it's like, it can be in architecture, but it can be in any other field. It truly requires interdisciplinary work because only when we try to look from a different perspective, if we can find answers, we can find new methods, approaches. So maybe also, I think that's a very good question that I could talk for hours about it. But my first interdisciplinary work and interdisciplinary research work was basically 20 years ago as a PhD student. So I'll tell you about my career. I finished my undergraduate degree in architecture, then master's degree in architecture, and then I practiced for a while. I worked in architectural profession, and then I realized that there were all of these questions that I didn't know how to answer. And even my kind of educational career was not very helpful to try to answer those questions. And then I decided to go into research and go back to school and obtain a PhD. And this was back at the time when interdisciplinary work was non-existent. So as a PhD student, I only took one class in architecture. Everything else was in other classes, in other fields: civil engineering, mechanical engineering, computer science, material science. Like, I remember taking a class on polymers through a material science department. I mean, it was a physical lab, white coats, goggles, safety goggles, and there was me, the architecture student, and I was working with material science students, essentially working on new types of polymer materials, understanding their properties. And I remember that the professor kept asking me, "What are you doing here? This is hard for you. Why are you interested in this?" And then I kept saying, "Well, I'm interested in materials. Like, I apply them in architecture, but I don't truly understand the properties, and that's why I'm taking this class." And every class like that, I always had to defend myself to professors. Why am I there from the architectural discipline? But going outside of the architecture into those other disciplines, those disciplines helped me learn how to think like a scientist, and how to kind of bridge the architecture, engineering, computer science, material science in a completely new and innovative way. And it basically set the course of my future career forever, because there are not that many people who understand. It's like speaking 4 or 5 different languages. The more that you know, the better off you are. So luckily, right now, interdisciplinary work is valued. We know the benefits of interdisciplinary work. So my suggestion to students would be, even if sometimes professors ask you, "Why are you interested in this? Why are you, I don't know, in civil engineering when you are, I don't know, an architect, or vice versa?" It doesn't matter. Just say, "Because I'm interested. I want to learn." So your education is your own responsibility in a way. So always strive to learn as much as possible as you can. Be hungry for knowledge, because knowledge cannot, I mean, once you learn something, it cannot be destroyed. And then I can certainly tell you that understanding different disciplines can only help you. And then who knows, like, if you try to imagine future, like near future, next 5 years, 10 years, 15 or 20, what is it going to look like? What future jobs will there be? I think more and more interdisciplinary work will be present in every sphere of society. So even if, even if your professors or the programs are quite rigid in terms of their disciplinary work, take your own kind of initiative and go outside of your field and try to learn something else from some other discipline.
I completely agree. This is something that the foundation is especially trying to put an emphasis on. And it was really great to hear that opinion from you and like such an in-depth response. So I want to wrap it up with one last question that is that regards the environment. So, what is your take on using recycled materials, for example, plastic, for building facades? Would that do more harm or good for the environment and people using them?
Yes, I think that's an excellent question too. So first of all, different materials have different properties, and then there's sort of a unit or a characteristic or property of materials called embodied energy of materials. So similar how every material has density, thermal conductivity, for insulation materials, for example, R value, thermal performance, and so on. There's also a unit called embodied energy of materials, and this unit or this value basically captures the energy that's embodied in the material from basically from the raw state, from manufacturing, transportation, and so on. And then over the last, I would say maybe 5 years, 6 or 7, we started paying more attention to materials, the nature of materials, their impacts on the environment, their impacts on health of building occupants as well. So those of you who are interested in materials and kind of the materials that are used in architecture and construction, Perkins and Will published a database of materials that are harmful to occupants. And if you just search for Perkins and Miller precautionary list or materials database, you'll find basically an online open source database of materials that are harmful for humans. And then there are many plastic materials included in that database. So when it comes to then using recycled plastic in building facades, when you reuse the material, you're actually essentially lowering the embodied energy of that structure rather than using a new material, no matter what the material class is. But I still think that we have to limit the amount of plastics, and it also depends on what type of plastic material it is. There are bioplastic materials out there that are not harmful, that have much lower embodied energy compared to some others. So I think as designers, architects, engineers, we have to pay more attention to this value, embodied energy of materials, and use that in our decision making when we're selecting different material types and applying them to building facades. The only problem is there's not a lot of data available. So we have data available for general classes or types of materials, for example, concrete versus glass versus wood versus aluminum, but it's typically very hard to find embodied energy of specific products. So for example, if you're comparing, I don't know, flooring material, tile A versus tile B, or for facade material, glass A versus glass B, it's very hard to find the specific data for those specific products because most of the time manufacturers do not even know what the embodied energy is. But hopefully in the future, the more that the industry is actually asking for this, the more we will be publishing and including and having databases available for that. So those of you who will be practicing in the future as architects and engineers, hopefully will be paying attention to the embodied energy in your projects.
Thank you so much. This webinar was quite motivating for me, and it was really interesting and it was really easy to follow. And I really liked how in-depth you were without getting confusing to us non-architects, non-civil engineers. So with this, I would like to conclude the webinar. Thank you so much for being here, and good evening.
Thank you so much. Good luck to everyone. Stay healthy.